So next, let's look at corollary 8 on page 235. We have R is XYZ is some kind of C1 function in the volume, and the volume in this case can be represented as from phi to psi. That is, the volume is Vxy. However, it doesn't say that it has to be YZ or XZ. So in other words, this is a less restrictive requirement than Theorem 8, which requires everything to be Vxy, Vyz, and Vxz, right? So this is less restrictive, the corollary is. And then phi size is C1, and then gamma is the angle between the positive z-axis and the exterior normal, as it always is. And the normal is sigma, which is the boundary of Vxy. In that case, then the triple integral over Vxy of R3 is going to be equal to the double integral of R cosine gamma over sigma. Now that is just a restating of the Theorem 8, where we prove this equal to that, right? And that is what this is saying right now. The difference, however, is that we only require Vxy. That's one big difference. And another one is so that makes things quite a bit easier in some sense. So let's turn to the next page. This result was proved above, okay, but then wasn't stated explicitly because Theorem 8, remember, in Theorem 8, in the proof, we proved that this part equal to this part, and similarly, this part equal to this, and that part equal to that. So Theorem 8 just says that the 3 added together equals to these 3 added together. But in reality, they are individually the same as well. So corollary 8 basically says they're individually the same, but with relaxed conditions. Okay, individually we only have to consider respective the phi and psi. So this of course works if your v instead of xy is vyz or vxz. Then it also works out as well in all three directions. So continue looking at the following page. It says that Vxy is not in general Vyz or Vxz. So then it need not be a sigma star. That's a big improvement. And then so this will be useful later when we need to subdivide things. And so anyway, so let's move on to example C on page 236. Where we have, what is that? Oh, we're going to redo example B on the previous page. Now, example B, but however, we are going to apply the new theorem to fit into example B. I mean, the new, So example B, we were supposed to integrate something, right? This thing right here. So we're going to use theorem 8 and let this our business equal to something in here and fit it, and then apply this theorem, so that way we turn the integral over sigma, which is the original problem, into the integral over v. Okay, and so please do that yourself. That is I think that is some kind of a substitution here, and you have to use the go ahead and plug that stuff in. And it works out pretty good because V is the unit sphere, which means you need to use the spherical coordinates. And remember that the spherical coordinates and formula is on page 211. And there's also Theorem 7 on page 211, which reminds you that to apply spherical coordinates, you got to add the sine phi and then r squared and stuff like that. All those details are on page 211 to refresh your memory. So once you plug everything, substitute it and plug everything, it works out very nicely. So please do that yourself, okay? And then we'll move on to example D. Now example D is, I find, first let me find it. Okay, example D, which is we are going to evaluate by two methods, some integral over triple integral V of something that looks somewhat simple. And we probably have done it before, where V is some kind of a region bounded by the planes x equal to 0, y 0, z equals 0, z equal to 1, and the cylinder and some cylinder. Okay, so that is the region that is a quarter of the cylinder. Okay, something like that. I drew a simple picture there. And then, so the book wants you to evaluate it by 2 methods. So that's what I did, okay? After I evaluated it by 2 methods, I find that, then I looked at what the book did, and the book didn't use either one of my methods. So then I did what the book, so that's my method 1 and method 2, which are the old way from basic calculus, and stuff came out very quickly, especially if you use the calculator. I don't remember if I probably used the calculator, yeah. Anyway, so then I went through what the book's method, which is applying the theorems we learned in this chapter or section or something, which of course is much more difficult. And so that's the rest of that, and that is there's more on the next page, okay? And so I ask you to do this example as a homework problem. That is, please do it like I did, okay? I just read the problem, didn't read any of it. It says 2 methods, so I came out with 2 methods to do it. And after you do that, then look at the book's methods and see if you can get it to make sense to you. And then do it in their way, okay? Then redo it the way they want to do it by using something. And then after you're done, and if it doesn't make sense, I just showed you some of the stuff I did. Read some of my stuff, see if that makes sense, okay? And then I will go over this when we talk about the homework in a moment here. So please do that as part of your homework, okay? And we will move on. And doing example D, which is, as you can see, it didn't take me long to do it, right? The first method only took about, a line? Once I typed it, because I typed it into the calculator. The second one, not much different, okay? I just write down the equation and then type it into the integral calculator to crank out what the answer is. But as you can see, so 2 methods each took maybe a line or 2, but actually the book's method, which is 2 methods, actually went all the way down here, plus some on the other side. So I find that doing this example D, example D very satisfying to be able to do things in different ways like that, even though it is longer, but it gives you a new way of doing old things. So which is why I'm having you do it, and because I believe you will find it equally satisfying. Okay, so let's move on to section 4.3 on the following page. When we talk about things like, let's see, 237, we'll talk about sigma star, okay? Now, we applied theorem 8 to some sphere in, what is it? Example C, right? It says that apply theorem 8. So I told you to apply theorem 8, and you probably did. But the problem is, theorem 8 doesn't apply. I mean, because the theorem 8 says theorem 8 specifically requires things to be sigma star, okay? Which is things has to be Vxy, Vyz, and Vzx, in which case, if you look at section 4.3, it says that surfaces sigma star are rather rare. Yeah, no kidding. A cube, if properly placed, has such a surface, but a sphere does not, okay? Because a sphere, it has along the edge, okay? The thing is not C1 because it goes to infinity or whatever. It's not going to happen. So, but we used it anyway because, we don't really mind that much. So, and what does it mean by a cube, if properly placed, has such a surface? So a cube is a sigma star, but if you were to tilt it like this, then it's not sigma star anymore. So it's not just the cube's work. You have to make sure the cube is sitting perfectly level, okay? Otherwise, it's still messed up. It is so, if you so much as turn it, your game is over. So that's why sigma star is rare. And however, there is a trick that we can use to make theorem 8 work by, well, the good old trick called cutting. Okay, let's cut this thing. Now let's consider the region region V is here's a eighth of a sphere. Oh, let's cut this thing. Cut the sphere. This is just the positive x-axis. The positive axis is part of the sphere. And then we have, which is defined, of course, by x bigger than 0, y bigger than 0, z bigger than 0, and then the sphere less than equal to 1. And this thing is not C1, okay? And we have already proved that it's not C1 on a couple of pages ago in example B, because when you take the derivative, it goes nuts around the edge of the sphere, that is along the equator. So but anyway, it's not C1. Well, theorem 8 is not directly applicable since each coordinate plane contains normals to the sphere. Yeah, it took a vertical dive, so that's why the derivatives go nuts. All right, so one way to decompose this thing, so we're going to cut it into parts. So as long as the parts work, then things will work better for us, kind of a deal. So to decompose the region is, so we're going to do this. So first we'll decompose V1 as the part of V that's inside the cylinder x squared plus y squared equal to rho squared, where rho is less than 1. So then, so it's a smaller part, fine. And then the rest of V is going to be subdivided into 3 parts by the planes x equal to square root rho over 2, y equal to square root rho over 2. So we have 2 planes here. And then that eventually cut this whole thing into 4 parts. Okay, we have V1, V2, V3, and V4. In such a way, now if we tie it this way, then V1 will be a VXY, as you can see it there. Okay, it has a vertical cylinder wall around it, but it goes from the XY plane to the top sphere. And then V2 is a VYZ, and it goes sideways, okay, or something. Let's see, XY, YZ. Well, anyway, work this out in your mind. That is V1 is a VXY. VXY means it goes up and down along the z-axis. Okay, phi is on the bottom, psi is on top. V2 is a YZ. That means the x is the top. The screen goes from back down to there, and then and so on. V3 is a x. Is a xz, so y is what's being varied, okay, and finally V4 can be a xz or yz. So, well, whatever. Please work that out in your mind yourself, and I would think V4, yeah. And anyway, things have to be such a way that their derivative has to be C1. That's the tough part, okay? And like before, when we were working this stuff, we only needed phi and psi to be what? Continuous. Now they have to be C1 all the way to the boundary, and that's the catch, okay? So nothing can go vertical in relation to this. So phi and psi, yeah, they cannot have vertical. Well, anyway, so please think about this a bit until it's clear in your mind why this is the case. And then we apply Green's theorem to each one. And then this will get, when we do that, then each part, when added, will combine to form a single triple integral over the entire V and a single surface integral over the entire surface, because any surface that's in common shared, okay, is done twice in opposite directions and cancel themselves out. And the surface integrals over the auxiliary surfaces, which we introduced, disappear in the end result from the fact that a normal in such a surface is at once an interior normal for one subregion and exterior normal for the adjacent one. That is, they cancel themselves out. So that Green's theorem then can be used to apply the complete square. In other words, we use the technicality and beat around the theorem until we got it to work, kind of a thing. All right, so that is that, and we have come to the end of this section. For homework, first please do example D, okay, on page 236 on previous page. Make sure you do that. I thought it's great fun to do it, and then the regular homework on next page 237. Please do problems, every problem except problem 9, okay. And so, in other words, do problems 1, 2. Let me show you my notebook here, which I have written down. Yeah, I can't, gotta find it. 230, what did I say page? Yeah, here it is. All right, so please, all except 9, so do example D, and then 1, 2, 3, 4, 5, 6, 7, 8, 10, 11, 12, 13, 14, 15. And so please do all that, and when you're done, I want to talk about some of them. So let's look at example D. It says that evaluate this general integral by 2 methods, which is what I did, okay? And I already showed it to you. They're very, very straightforward, right? It just, the first method is the old-fashioned way. The second method, I just put in, what is this, cylindrical coordinates, okay? Still pretty straightforward and old-fashioned. And I typed everything into the Desmos integral calculator, and I got these 2 integrals to come out very method, what is that? Yeah, method 1, okay, and that equals to 11 over 24. I tried the cylindrical methods, and that also equals to 11/24. So I'm looking preachy, right? And so that is that's that. So next, I look at the book, and they are doing it rather differently. And the first thing I need to figure out is what are they doing? Okay, so what I figured out is what the book is doing here. It says, the book says by iteration. What iteration? Is on the previous page, page 235. Okay, this part where I marked as A. That is, as part of the proof, it says that the double integral is, the triple integral is the iterated integral from phi to psi, right? This part, and that's the part I'm using, which also equals to this. So I use that, which turned out to be what the book is doing. That is, and I'm also using the theorem though. That is, I let R3 equals to X, the formula inside, and let P and Q equal to 0 in the, let's see, what are we talking about here? Yep, in theorem 8, okay? So applying a theorem 8, we'll let R3 equal to that, and then integrating, that means R will have an extra Z in there somewhere, and various extra Z's. So then the triple integral, then applying that formula will be equal to the double integral integrating from phi to psi. And then remember, Z in this case, the phi and psi are equal to, one of them, because we're integrating that, where's that thing? Yeah, from the cylinder from bottom to top, phi is just 0, whereas psi is just 1. Okay, phi is the 0, Z equal to 0, psi is equal to 1. Now, so when we plug that into this equation here, we get the integral equals to Z equal to 1, the 0, 1 disappears, and then Z equal to 1 again, we get y over 2 and x over 2 ds. So we got to this point, and that is what the book has, right? So I equal to, yeah, so that's where the book got this got to this part, that y equal to, let's see, what does that say? Doesn't matter. Where R equal this thing integrating over R over X, where R over X is this stuff that is the bottom of the cylinder that got quartered. So it looks like that. And once we have this thing, then we just the next step is just to plug in the cylindrical coordinates, because we are working on the cylinder. And let's see, let me find it. I'm looking at the wrong page. Okay, here's better. And then next step is we need to plug into wait a second. Yeah, I got it. Okay, so then we have the formula down. So we just have to plug in the cylindrical coordinates, which is our cosine theta, our sine theta, and ds is our dr d theta. And in this case, and plugging everything in and then integrating let's see, what are we integrating here? Oh yeah, well, whatever, okay? So angles goes from 0 to pi over 2, r goes from 0 to 1, and we're integrating over the entire bottom region, Rx. Rx is drawn right here. So then when we plug everything in and doing the integration, it equals to 11 over 24, which is what you see, I plugged all that into the calculator, method 3, which is the first method in the book. Okay, I typed all this in, and the Wolfram calculator says that equals to 1124 after, well, yeah. So that is good, and that's method 3, which is the first method in the book. So next, let's look at the next thing. The next method is, well, the previous method, we did use Theorem 8, but this method, we are going to use Theorem 8 again, in a somewhat different way. So this time, method 4, we are going to allow to make the stuff in the book come out. We'll let P1 equal to xy. Remember, the formula is, this is the formula, the thing we're trying to integrate up here, right? So we'll let P1 equal to xy, line them up. Q2 is equal yz, and R3 equal to zx. So that the whole thing will, in Theorem 8, which means the whole thing will look just like the theorem. Because Theorem 8 says, Theorem 8 says that this integral, right, is we'll just plug each part and assign it to be P1, Q2, and R3, which is over dV. Then we can translate it into this thing that is over d sigma with a bunch of cosine, alpha, beta, etc. in it. And that's what we're doing right now. So if we do that, then let's see, let me find it again. Okay, so we have P1 down here. P1 is xy and yz and zx. So then we integrate, okay, then P will be x squared or y over 2, etc. Okay, and then the integral we're looking for is now P1, Q2, and R3 dV, which is by Theorem 8, then it translates to the integral over sigma star of P cosine alpha, Q cosine beta, and R cosine gamma. And then, okay, that's good. Now we're going to calculate the integral on each surface, because we're now integrating over the surface of this object. So let's calculate it on each surface. Now the integral on surface 1, that's the vertical wall for the xz plane, y equal to 0. Okay, so and cosine gamma is 0. Therefore, when you look at that, the bunch of y's is 0, and then when there's no y, cosine gamma is 0, so the integral is 0. And then similarly for the next one, the integral is for the vertical plane here the yz plane is integral also 0. Now on the bottom, z is 0, and cosine alpha is 0, so the integral is still 0. So we have three things, three surfaces where the integral is just going to be 0. So that means, let's see, so that means we have the top surface left, right? So we did, so what is the integral on top? Then we just put on top, z is constantly equal to 1. So we integrate this thing with z equal to 1, and in rectangular coordinates, cylindrical coordinates, right? So we integrate this thing over the top surface, okay, only the top, where z is constantly 1. So then that's z squared is just 1, x is our cosine theta, plug it in and do the integration. And I think I did this one in my head. I didn't even bother typing it into the calculator. And that equals to 1/6. All right, so that's the cylindrical surface. That is the bottom surface. So now we have done three surfaces, surface 1, 2, I should show you this. Surface 1, 2, and bottom, okay? Bottom and, let's see, surface 1, 2, bottom and top, right? Let's see, surface, give me a second here. Surface top. 1, 2, bottom, and top. Yeah, so we did 1, 2, and bottom, top. So, but we'll have one more surface left, and that is the cylindrical surface. And to calculate that, we have, I calculated what these things are. That is the cosine alpha on the cylindrical surface. If you do the, I don't know what that is, the vector or something, but eventually you calculate the x. X over 1 is cosine alpha, y over 1 is cosine beta on the cylindrical surface, and cosine gamma is constantly 0. And here's the picture to figure out why that is the case. Why is my camera not focusing? I'll wait for it to focus a little bit. There it is. Okay, so that is out of this picture. Okay, and then I plugged it in again using what is this? Cylindrical coordinates, and plugged in the integration. I calculate the integral. This is the integral. Okay, I plugged in and y and x as r cosine theta. R is constantly 1, so we don't have to worry about it. So calculating the integral to be 7/24. Now, so then previously we had 1/6 plus 7/24, and that equals to 11/24. So again, I got the 11/24, and that's the fourth method. And then I looked at the book, and the book said something different from what I did, okay, in calculating the cylindrical surface. So when I looked at it more carefully, I realized that the book is applying Theorem 7. This is about Theorem 7, is to calculate the cylindrical surface. We still have the same integral here. Let's see. Oh, I forgot to mention that when I said that when I calculated this thing to be end up being 7/24, I did it on the calculator, and that which says right here the method 4a, the second part, my solution. Okay, see this is the integral, and when I typed in it, it says 7/24, and the other answer was 1/6, and together it becomes 11/24. So that's that. So next, let's look at what the book did to do this. Okay, the book did it differently. The integral, what the book did is in order to integrate this thing, that's what we're trying to do. And so instead of what I did, the book applied Theorem 7 on page 223. So let's look at Theorem 7 again. Theorem 7 says that we're going to, we can integrate things. Let's see. Yeah, anyway, so Theorem 7 uses this rule, right, where we have this thing is the secant gamma, and or it can be secant alpha or beta, depending on who is the independent variable here. Okay, in this case, z is equal to fxy, then this is secant gamma. If you have used x, then it would be alpha or something like that. So to apply that, to apply Theorem 7, what the book did is, here's our integral. Yeah, let's see. Here's our, we're plugging in our original integral, okay? And what we're doing is, let's see, what we're doing is we're gonna split it into, two integrals and apply each one between the addition sign, and then apply each one with Theorem 7 separately, but in a similar way. So we do that, and so this part becomes secant alpha, okay, in Theorem 7. This part, because this part x is equal to fyz, and in this part y is equal to fxz. So secant beta will be the radical here, and then we do the same thing. And to evaluate these things, we have we end up have this integral here, and this equals to 1/8, and this integral here end up being 1/6, and the total adding to, it was 1/6 before, and so total it becomes 11/24 again. So let me show you the integration that I did. We have right here so here is the final amount. This is much easier to do. Okay, I typed it in, and one of them is 1/6, and the other one is 1/8. And you might think, oh, these two integrals look symmetrical. Why would they be different? That's because the dz is on this side, whereas the dy is Well, it's let's see. The integration, the order is somehow different. Okay, we're integrating z first, then x, whereas the other one we integrate y first, then z. And anyway, so this is what I typed into the calculator. Okay, so it is guaranteed to be correct because I just copy and pasted this. This is the calculator result, so it can't be wrong. And anyway, but the point is, it all worked out to be the total is 1/6, just like the book says, and the total is 1/6 plus 1/8, and where's, let me find it. I lost the page. Yeah, the total then is 1/8. Okay, I had 1/8 and 1/6, and then previously there's a 1/6 in here, so it all add up to be 11/24. So that is all correct. Oh, and I should mention that in the second method, that is in this stuff that we're doing over here, and let's see, where's my hand? Right here. In this stuff, we only did cosine alpha and cosine beta, whereas the original formula has the cosine alpha part, beta part, and gamma part. But the gamma is 0 on the cylindrical surface. Okay, it says right here, cosine gamma is 0 because it's is 90 degrees to the z-axis, which means the cosine is going to be 0, so we don't have to calculate that part, which is why we only calculated these two integrals separately. Now that sounds like a lot of work, right? But I think it's great fun to show how Theorem 7 and Theorem 8 works, and also know that we got the right answer because we know how to do this stuff from way back. So now if we get the same, still get the right answer, that means that we are probably on the right track. So that is example D. Oh, I also want to remind you that when you type stuff into the Wolfram calculator, be careful with spacing. That is, sometimes if you type in XY, it might, if it says, I don't know what XY is, that's because it requires a space to mean multiplication. So, and then other times it doesn't. I don't know. Like this one, it was okay. Okay, let's see what I'm referring to this, like r sine x, there's no space here and it didn't complain. I don't know, just pay attention to these little details, and otherwise it'll tell you, I don't know what you're talking about, and doesn't say why either. So then you think that maybe a formula is too hard, when in reality, it just it wants you to put a space in it. So next, let's do problem 1. We're going to check Green's theorem by if P is e to the power x, and then Q and R is 0, and V is is the standard tetrahedron. Okay, so let's do that. We have I have written down here. We have to check Green's theorem on both sides. Okay, calculate both sides of, here's Green's theorem, and we're going to calculate both sides independently. Well, somewhat. Anyway, so then remember that, so P is e to the power x, P1 then also e to the power x, then the triple integral of V will be P1, where Q and R is 0, is we plug this thing in, is equal to e to the power 5 halves. And as I typed this into the Wolfram calculator, and it showed me the answer very nicely. So I want to show it to you, even though there's no real reason to show it to you. Okay, so there's that. There's that, and that's the left side. Now the right side, we integrate over the surface, and that is a bit more complicated. Mostly we need to remember that the cosine alpha is 0 on the vertical or on the axis planes. The cosine alpha is 0 on both the xz and the yz plane, and we're integrating with a cosine 0 in there, so we can ignore those planes. So we only have to integrate over these two planes. That is sigma 2, which is the triangle on the yz plane, this one right here, okay, and then sigma 1, which is the slanted plane. Okay, sigma 1 is x equal to 1 minus y minus z. So we're going to do this integration right here over sigma from sigma 2 and sigma 2 and sigma 1, and then add them together, I guess. So then calculating each one, let's see. To calculate these things, we're going to apply Theorem 7. Okay, that's the one with the radical in it. and then we have to calculate f appropriately. So here is the first integral where the integral, the radical, it just happens to be 0. So the integral comes out pretty good. Okay, and then so then the second, and then the other one we have the integral over sigma 1, which is slightly more complicated. So we have the radical, which end up being something, the cos, and but anyway, it equals to e minus a half. So then we have the whole thing, was it added or subtracted? Well, the total, then it becomes, I guess it's sigma 1 minus sigma 2. Yeah, that is what I have right here because of the directions. Okay, the direction of the outward normal, one's pointing up and one's pointing some other way or something. Anyway, the integral is calculated by sigma 1 minus sigma 2. So then this is, let's see, sigma 1 is e minus 2. And then where's sigma 2? Sigma 2 is up here and equals 1/2. And so once you do the subtraction, it becomes e minus 2.5, and which is e minus 5/2, which is somewhat tedious, okay, but it's still an interesting, a nice way for us to use Theorem 8 and get a feel for it. So, so it does come out. And in doing so, we have to work on with Theorem 8, but we also need to use Theorem 7, okay, where we have to calculate f1 and f2 and take the square root of 1 plus f1 and f2. I'm talking about this thing in Theorem 7. You need to plug this in, but this thing right here. Okay, and remember this formula works if it's z equals to fxy, or if it's x equal to fxz, x equal to fyz, or y equal to fxz. Doesn't matter who equals to what. Okay, it all works out. You just have to adjust accordingly, like which angle is up. So that is what I did here. That is, I have a note here that says replace gamma as alpha when needed, because the slanted surface, which is I represent it as x equal to 1 minus y minus z. So this is fyz. So then f1 is minus 1 and f2 is minus 1 in the formula where we need to apply Theorem 7. We need to not forget this thing right here. Okay, plug that into the formula and everything comes out very nicely. For problem 2, we have to do the same thing, okay, with p equal to x squared and v is the unit sphere. Okay, so I have that here first. We just do it the old-fashioned way on, here it is. All right, we do it the old-fashioned way. We plug it into the triple integral, right, with v being the unit sphere, that should be fast enough. And then use the polar coordinates, which is on page 211. Well, don't forget the sine phi, and then there's an r squared, right? And then once you plug this formula into the Wolfram calculator, it will give you the answer like I have right here, which is happen to be 0. And okay, that is what the calculator says, so I believe it. So that's that. And then the other side, we have to do the surface integral, in which case we're going to subtract by this using the principle on page 235 in Theorem 8. That is this thing right here. Okay, we're integrating where this thing is the top surface, where phi is being subtracted by psi is a minus phi. Okay, good. So we have this situation right here. Applying this formula, we have let's see, we're in problem 2. Okay, so we do this subtraction, page 235, okay, where this thing is being subtracted by this thing. Now, but they are, when you do the subtraction, they are actually for sigma 2, x is a minus, and then but the secant is also minus. So then these two actually have the same value. So when you subtract, they equal to 0, just like which is what is said in the first method. So that works out. And just to remind you why it equals to 0, this is said on page 234 down here, where secant cosine is less than 0, and then this thing is also less than 0. So you have two negatives that that becomes a positive. So then as a result, the top half integral happen to be equal to the bottom half. So the subtraction makes it equal to 0. Okay, that negative signs always give me a headache. So that should be good enough. Let's not think too hard and start hurting, getting hurt by the negative sign. Okay, positive, negative. So let's move on. So next, let's consider problem 3. We have, we're going to suppose to redo example A by projecting sigma 1 on it and sigma 2 on the other planes, which is fine. Okay, that should be straightforward. I did it right here. Not much to talk about. You just pay attention to the integral limits. And then, you do have to apply theorem 7, that is calculate the partial derivatives, that is what's under the square root, the secant gamma. Okay, so as I have done here, we have, for example, the first one, x will be equal to 2 minus y, which is a function of f, y, z. So f2 is 0, f1 is negative 1, and you plug, so that gives us a square root of 2 in here under the radical, and then do the integration, and that should come out to be the right answer. And then similarly with the other one, where we have z equals to fxy, which is y over 2, which gives f1 is 0, f2 is 1/2, and plug it into theorem 7. And they also come out, this answer also proved to be correct, and that is that's problem 3. Problem 4, we have, let's see what it is first. Problem 4, we have, we're going to calculate this thing, which looks all symmetrical, okay, over sigma, where sigma is the part of the cone that's cut out by some cylinder. Now so I plotted this in the Desmos calculator and see what the cone looks like. So and then but I didn't really do a picture of it. Okay, the cone got cut out by the circle, looks something like that. Okay, there's a top piece and a bottom piece, what the book calls naps. So that's the top nap and the bottom nap. Okay, so anyway, we have the two pieces. We are going to integrate over both pieces one at a time. The bottom region, the shadow region, that is the cylinder that cut out the circle, the cylinder is also represented in polar coordinates as 2 cosine theta. Okay, that can be done, I don't know, you just, do x equal to r cosine theta, etc., and to come up with this thing. So anyway, r is equal to 2 cosine theta. Bear in mind that. So let's integrate over sigma 1, and this is applying again the theorem 7, where we have to do the radical. Okay, that is so f1. So this is z is the square root of x squared plus y squared. That is the whatever that is the part of the cone. So here's f1, here's f2, and then here's the radical for theorem 7, which end up being square root of 2, which is convenient. Okay, so then the integral, we plug everything in, and then change it to polar to cylindrical coordinates, or polar. Which one is this? Just polar, I think, not cylindrical. And don't forget the RDR, okay? Otherwise, this answer will not come out. So then, polar coordinates, plugging things into the polar coordinates where. Remember, r goes from 0 to 2 cosine theta because that we're integrating inside that circle, the cylinder thing. So and the cylinder is r equal to 2 cosine theta. So that's where r goes. And so once we do that integration, that equals to something worse. Equals to. Okay, it equals to right here. I wrote the answer on this side. Okay, and where did I get that? Of course, I got it from the Wolfram calculator right here. Here's the integration. Okay, I typed all that stuff in, and as you can see, it says that that equals 29 pi over 4 square root of 2. Now, the integral over the bottom half is has the same value because again, because some negative sign, and sigma 2 is minus, and then something else is minus, and it becomes a plus or something. Let's see. Yeah, but the fact that it's negative means nothing, because in our function everything's getting squared and stuff. Okay, so well, we don't care if it's minus. The point is it all come out to be the same. So the top piece and the bottom piece give the same integral. So the total is double of what we found before, which is this answer, which is correct. So that's good. Okay, next let's look at problem 5, which says the moment of inertia's formula should go like that. Well, it did already say that on page 232, okay, where it says right here, the moment of inertia is y squared plus z squared, which is r squared, times the sigma, which is the density, and integrating over surfaces. So that is exactly that, and that's all I have to say about it. Right? And so that is problem 5, see? And y squared plus z squared is r squared. So let's move on to problem 6, where we're spinning some empty sphere around some axis. Okay, so then following that formula we just saw, it equals to the double integral of over sigma y squared plus z squared, and times density and d sigma. Now to calculate this d sigma thing, we have to apply theorem 7, where we have that radical. Okay, and this radical right here we need to calculate. So then by theorem 7, the function p will be used as the y squared plus c squared times whatever is in here. Okay, in theorem 7, and z is equals to the square root. That is just the first half of the hemisphere, and we're spinning it around the x-axis. So we only calculate half of it and then double it, because the first half, we're spinning this thing around the x-axis. Doesn't matter if it's the top half, the bottom half. If we add it up, it should all come out. So we're doing only half of it, and so bear that in mind. Now we have so plugging stuff in, we have this formula where so we have y squared, and then z equals to this, right? So then z squared will be equal to this thing, and the formula cancel out somewhat, and then I will change this to polar coordinates. Okay, again, don't forget r dr, and and the x is r cosine theta, and then the subtraction here becomes, is that a division? Well, I think it is, but anyway, that becomes this is the square root is in there somewhere, okay, equals to a over z. And when all the dust settled, we have to integrate, I believe, this thing right here. This thing has to be integrated. Now that doesn't look so bad, except that when I typed it into the Wolfram calculator, it couldn't do it, okay, because I have too many variables. I have variable in the limits, and I'm integrating from 0 to a, which and then there's a bunch of, anyway, I couldn't get it to work. So I was forced to have it only integrate this part, ignoring this part outside, and then I had to do the outside myself. So once I have it do only this part, and then it was able to give me the answer that I will show you right here. Integrating, only doing the inside integration, which Wolfram was able to tell me what it is. And we can do this ourselves too if we're integrating with only r. Everything else is a constant, but there's a square root on the bottom, and then there's other stuff, and let's not work that hard. Wear ourselves out. So then the integration, according to Wolfram, equals to this thing. Okay, then I did the rest of the integration, which turns out to be not that bad, because a lot of stuff became 0 when I did it. Okay, the first part is already 0, and then the second part, the integrating cosine 2x, that's the only part that has the x, not x, this is cosine theta. Let me fix that. Well, when I type stuff in the Wolfram calculator, anytime there's theta, then I replace it with x so that it's easier to type. All right, so we do the integration, and this part, remember the integral from 0 to 2 pi of cosine 2x is 0, okay? So that part is also 0, so all that we have left is this thing times this thing, okay? When the negative signs cancel out. So when I get that to come out, that would eventually be equal to this, because the mass is 4 pi r squared times density of the shell. So then all said and told, it does equal to this thing, which is what the back of the book says. So that is correct. Next, let's consider problem 7. Problem 7 is similar to what we did previously when we had in the previous section when we had short formulas for the area. That was on page 225. And this is no different. Now we have short formulas for volume, and that works exactly the same way. What we're going to do is apply theorem 8 and let the first formula, let P1 equals 1, the other Q and R be 0. So then the integral of 1 dV will be exactly that thing, okay? And similar for Q and R. And then if you add the three things together, it will be all three things added together, divided by 3 is also the volume. So you can calculate it that way. So that's problem 7. And then next problem 8, we're supposed to calculate the volume of some tetrahedron. And so we are going to, let's see. So we have the volume of the tetrahedron is going to be double the integral over sigma of z cosine gamma. Well, that's by applying the one of these formulas. Apply the third one, okay? The z cosine gamma business. And then we z cosine gamma, we have, that will be equal to gamma 1, the integral on gamma 1 minus sigma 2 minus sigma 1. Yeah, so sigma 2, when you integrate it, it equals to 1/6. The integral on sigma 1 is just 0. And then, and I didn't say anything, well, doesn't matter, okay? Because we only care about the gamma 1. So that is, that checks out to be correct, and that's problem 8. So next, let's look at problem 10. We have this problem looks almost identical to the problem 14 on page 227. So we're going to do it in a similar way. First, we need to figure out what is the directional derivative. The directional derivative is given on page in the book, page 81. Okay, theorem 7. So I just copied it right down here. And once we have that copied down, then we're good to go. So the double integral over sigma star would be, there's a u on there, so I slap the u on there just like it wants, which then that equals to the double integral, p, where we call p as uv1. Okay, we'll name p as uv1, q as uv2, and so on, so that it looks just like the theorem 8. So by theorem 8, then it equals the triple integral of p1, q2, and r3. And then we calculate what is p1, q2, and r3, and then substitute it in there, and that ends up to be exactly with the formula that the book is looking for. If triangle V is equal to V11 and then V22 and then V33, and you add up the stuff and it all comes out nicely. Okay, that's problem 10. Now problem 11, 12, and 13 are directly deriving from problem 10, so I won't talk about it too much. I will just show it to you if you have any questions. And then I'll move on to problem 14. Okay, next let's do problem 14. Let me write it down first. So problem 14 says the proof that the surface integral is 0 for every surface sigma if P1 plus Q2 means that P1 plus Q2 plus R3 equals to 0. Assuming that is somehow integrating every surface and force it to be 0. It's 0 no matter what. Then P1, Q2, and R3 has to be 0. Now to prove that, we have suppose this thing is this the surface integral is 0 for every sigma star, okay, which means the triple integral of volume will be 0 for every volume no matter how small it is. And that means P1, Q2, and R3 has to be 0 because let's say it isn't, okay, let's say it's bigger than 0 in some small neighborhood, a 3D neighborhood where a small volume where the triple integral is bigger than 0. Then but if this function is bigger than 0 in the entire neighborhood, that means the triple integral has to be bigger than 0. That's by the mean value theorem. Okay, so then this value has to be 0, which means that well, yeah. So we have proved it. Of course, proving the other direction is there's not much happening there. If P1, Q2 plus R3 is 0, then by the theorem 8, then the surface integral is 0 as well. So that's problem 14. Now problem 15, let's look at that. Problem 15, we'll let sigma be some kind of a surface z equal to phi x y, which is bounded by a closed curve, okay? Now, and then we assume that P1 plus Q2 plus R3 equal to 0. Then the integral, the surface integral over sigma of P cosine alpha, Q cosine beta, etc., that is the integral in theorem 8, has the same value no matter what surface we're talking about. So as an example, let's say we have two surfaces. I have it graphed right here. We have, see, the bottom surface, let's say the red one, okay, we'll call it z equals to phi. And the top surface, we'll call it z equals to psi. Now, these two surfaces, one goes one way and one goes another way. But the integral around them is going to be the same. The proof of that comes from, so here's my proof. Let's see, let sigma 1 be the bottom surface, okay, with the boundary gamma, and then sigma 2 be the top surface with the same boundary as I show you in that picture, okay, the two things share the same boundary, and let's say that phi is completely less than psi, so that we can have a volume in between that they don't intersect for now, okay? So the book doesn't say that the two surfaces can't intersect, but we're doing that for now, and we'll fix that in a moment. So let's say one is completely less than the other one, like my picture shows, so that it encloses some volume. Then by theorem 8, let V be the volume between phi and psi, then the triple integral is P1 plus Q2 plus R3 equal to 0. But the triple integral is also equals to the double integral of sigma 1 minus sigma 2. Okay, this is again from that formula in the proof of theorem 8 that we've used several times already. That is this part, and that is the triple integral equals to the sigma 1 minus the sigma 2 of this kind of integrating. Let's see, which one am I using? I think I'm using this one. Okay, that one minus that one, not the one with the cosine. We'll just do this one, this part. So so then that means the top and actually I have the whole thing written out. Well, whatever, we'll use the bottom. The point is that the 0 equals to this integral, okay, with the minus the other one, so they are the same. Is that what we're proving here? I'm forgetting what we're proving here. Let's see, where is it? Cosine, yeah, that is exactly what we're proving, okay? We do need a cosine and stuff. So we're using that part of the proof of theorem 8 and to show that these two integrals over sigma 1 and sigma 2 are the same. So, and yeah, so then they are completely the same. Now in using this, however, we're ignoring the part of theorem 8 where it says root 2, where it says the volume bounded by them has to be sigma star. We'll just let's say it is or it isn't or something. Let's not think too hard about that because the book didn't really say that much. So we'll just assume that theorem 8 applies and not worry too much about whether the volume is bounded by sigma star or not. But we still have to be concerned, what if phi and psi cross each other or reach it or something? You know, they're not just this, they're not just conveniently bounding two surfaces like that, like my picture here, where they don't touch except on the boundary, right? What if they even cross each other? Then we have complications. Then what we're going to do is then we're going to compare them to a third surface. Okay, I draw a third surface that's clear up there. That does not touch phi or psi. Okay, that's eta right there. See equal to eta xy, the gray one, and then. By what we just proved, being that theta doesn't touch either one, then the integral over theta, eta, anyway, the gray surface, integral over the gray surface will be the same as integral over the green or the red one, right? They will be equal because of what we just proved, being that the gray surface doesn't touch the other two. And therefore, so here's my last part of the argument. If phi crosses the psi, then we choose some kind of eta that such a eta is bigger than both of them by far. And then then the eta will be equal to phi, the integral does, which is eta also equal to psi, then therefore phi equal to psi. And yeah, so that is the basic equality. What is it called? I don't even remember what it's called. But anyway, when A equal to B, B equal to C, that means A equal to C argument from way back when. And that marks the end of this section. Oh, I forgot to show you the entire picture of what I drew here. I think this thing looks quite cute. Okay, and those are the formulas I used to draw this thing. And not that you need to draw it necessarily. I just thought it's fun to draw this kind of stuff. All right, that's it.